Method 2 takes us away from FFT. Okay, good. Get a better pen here. Polynomial expansions. And this is kind of a pretty simple thing to think about. I'm going to take a function, and I'm just going to say, look, if this function f of x, I'm going to chop it up into n plus 1 points. Equally spaced is what we've been doing. So you take this function, you say, I'm going to divide it up in a certain number of points, and what I can do is say, well, I want accurate ways to represent the function, the points. So I could say something like this. Well, how about if I just say, well, I'll do a polynomial representation of this function, like so. Put a polynomial to it. That's not a big deal. In fact, I get to pick A0, A1 all the way through A of n. So I can pick these so they exactly go through the function points they're supposed to at each of my discrete points. Okay? All right. So the finer I chop this, the more n's I use, the more n points, the bigger n is, then the more accuracy I get. Okay. Great. Now, what's the problem with this? You know how the story is going to build, right? Eventually, I'm going to get to a method where I say, hey, there is no problem with this. But for everyone before that, I'm going to say, what's the problem with this? And the problem with this is the following. This is a n plus 1 degree polynomial, right? Let's talk about what polynomials do. So let's say, so I have, actually, let's call it an nth degree polynomial. I have n plus 1 points, but it's n degrees. Right? It's whatever the highest this is. So, yeah.
How do you know the n is exactly equal to the amount of points that we chop it like?
So what I'm going to do, let me try to see if I understand your question. I have some function f of x, say from -1 to 1. And I'm just saying, I know what this f of x, say, originally is, exactly. But now I'm going to start doing computing with it, calculating derivatives, putting in ODEs, so forth. So I've got to discretize a certain number of points. So I'll just evenly cut up the domain and say I want my values to go exactly through that curve. Right? So I know the values of this, so I can set this up as a giant system of equations. So what are the unknowns here? A0, A1. I have n plus 1 unknowns. I have n intervals, so I chop this up into, here's my n plus first point, here's my first point. Chop these all up. So I have a constraint here. Has to satisfy this, this, this. So I have n plus 1 constraints, n plus 1 unknowns. Solve ax equal to b. I got them. By the way, there are faster ways to compute A0, A1, A2. These Lagrange polynomials is, for instance, 1. We're not going to talk so much about them, but there are fast ways to compute how you should build this thing. But here's the thing about n-degree polynomials. First-degree polynomial. Let's talk about that. Okay? It's like a line, right? A0 plus A1x. What does the second degree look like? Parabola. Yeah? You remember doing parabolas in 7th grade or so? Is that right? About right? Is that 7th grade? You're drawing parabolas. Okay, I do remember that. And I was like, partly, and I know what parabolas are, but back then I was like, that's stupid. Junior high, why would you care about parabolas? But now later in life, you understand how important they are to your being. Okay, good. All right. N equals 3. N equals 4. Huskies. Okay, hopefully we win this weekend. Otherwise, it'll be a 500 season. But if we win this weekend, we can call it all good, right? We'll have. All right. Anyway, maybe you don't care. But there we go, polynomials. Now I want to point out something. How many turns do polynomials take relative to the degree? So n minus 1 turns, right? So second degree polynomial takes 1 turn. N equals 2, 2 turns. 4, 1, 2, 3. Ooh, okay. How many degrees was this? N. How many turns does it take? All right. That's the big deal with this. And that's the problem with this. So let me give you a function. And you can see it there in the notes. Let me actually write down exactly what it is. And we will draw as best we can. Let me correct that. I will draw as best I can. Although maybe I could take volunteers for it. That'd be pretty good. This function here, which is 1 over 1 plus 16x squared. And if you plot this thing, this is just basically like sort of parabola-ish looking. Now, we're going to do the following. We're going to do polynomial fit to this, right? So we're going to say, all right, put a bunch of evenly spaced points on this thing, and so forth. Now, look at that function. How many turns does it really have in there? Kind of one. It's trying to do maybe 2 others here. Now, suppose I break this up, for instance, into, I think I do here, 12 points or 24 points. Let's just make up some number. Let's say I try to break this up into 30 points. Which is not a whole lot. How many turns does it have to take? 29. It has to. All right. So what's it going to try? This is a problem. It should only have, it's a simple function. You know, it only wants to do 2 turns, really, 2, 3, maybe. And you're telling it to do 29 turns. So it's going to, but it has to, by the way, you will get a polynomial that will fit exactly at the function points at those dots. But what does it do in between? Let me show you here. Okay, so it goes here. It looks just great. It looks just great. It goes, oh, I got to take 29 turns. Oh, I'm screwed. Yeah, and then it does things like that. That is your polynomial fit to this thing. Does that look good? It's awful. In fact, the higher the n you take, the worse this thing gets. So that at the boundaries, you can do things like this. By the way, great in the middle. Fits beautifully. And then out at the edges, kills you. Polynomial wiggle is what it's called.
Is that consistent that in the middle it's okay, or is it just like take those wiggles wherever, it varies the function?
Yeah, generally, it always works really nicely in the middle. It's just at the boundary where it really has problems. So it's called polynomial wiggle, and it kind of kills you. You can't use this technique. It seems so nice. By the way, here's the interesting fact about this, and this is what's deceiving. Suppose I say, how well did my approximation do to my function? Right? You could ask that question, and normally you'd have to, instead of just looking, nobody just looks and says it does well or not. You have a measure. And typically, how do we measure error? We do a least square fit, don't we? We say, take the difference between the point that's supposed to be and the point I actually calculate, square that, divide by the number of prompts, right? You can do this E2 fit. This is something like this. And it's, you give it the actual points that it's supposed to be at minus what you calculated over the total number of points. That's the least square fit. And by the way, your error is going to be exactly 0. So you'd say, oh, by some objective measure, it says you did awesome. And then you plot it and you go, you did not do awesome. Okay? So it's important you realize that's going on, even though your error says, man, I hit every single point I was supposed to. Okay? All right.
I'm sorry.
Yeah.
So this would be an effective method because you use the Chebychev polynomial.
Well, so this
in that form, that's good because
if you're in this form, so if you take a Taylor series, basically, on an evenly spaced domain, you will always have a problem with the fitting at the boundaries. You always get this polynomial wiggle issue, which, by the way, it's a lot worse than even method 1.
Okay, but I mean, okay, so you're saying that the two polynomials, it's not you knew that you could make it in polynomial form. Like if you had a pure polynomial, then you'd be set spectrally. You could use spectral methods.
Well, we're going to talk next about spectral methods here, which is method 3. So we're going to take a twist on the polynomials.